On March 11, 2011, at 2:46 in the afternoon, a fault segment roughly 500 kilometers long beneath the Pacific Ocean off northeastern Japan slipped between 40 and 60 meters in under 3 minutes. The energy released was equivalent to approximately 9,000 Hiroshima bombs. The seafloor above the fault rose by several meters, and that rise transferred directly into the ocean above it. Within minutes, wave crests were moving toward the Tohoku coastline at the speed of a commercial jet aircraft. When they arrived, they were between 12 and 15 meters high. In some locations, they ran further inland than anyone's instruments had been positioned to measure. The walls Japan had built to stop them were designed for 8-meter waves. They were overtopped in seconds. In several documented cases, the water crashing over the top of those walls fell with enough force to knock the structures apart from the landward side. More than 20,000 people were killed. Entire cities ceased to exist at the resolution they had occupied the morning before. The Fukushima Daiichi nuclear plant lost its backup generators to the flooding and entered a meltdown within days. Japan had been building coastal seawalls for decades before 2011. The city of Kamaishi had what was then the largest seawall in the world, a structure that took 31 years to complete at a cost of $1.6 billion and which sat at the entrance to Kamaishi Bay. The 2011 tsunami overtopped it in minutes. Roughly 1,000 people in the city died anyway. That outcome did not mean the wall was irrelevant. It meant the wall had been designed within an understanding of the threat that the 2011 event rendered obsolete. The question Japan faced after the disaster was not whether to build walls. It was how to build walls that do not give people reasons to believe the ocean has been solved. Answer that emerged from years of wave tank experiments, geotechnical surveys, and engineering review was a seawall system that explicitly does not promise to stop the largest possible tsunami. It promises to reduce the destructive force of a medium-scale tsunami by 30 to 50%, and to delay wave energy long enough to give residents several additional minutes to move to high ground. Those minutes are the design specification. Everything else is engineering in service of that number. The walls now rising along the Tohoku coastline in Iwate, Miyagi, and Fukushima prefectures stretch roughly 395 kilometers, with plans to extend the network to 430. The tallest sections reach 15.5 meters above mean sea level. The foundations beneath those sections descend 25 meters into the coastal sediment. The base of the widest sections extends 50 meters at the foot, narrowing upward in a trapezoidal profile that distributes horizontal wave impact across the full mass of the structure rather than concentrating it at any single point. Before any concrete is poured, the coastal sediment must be made capable of holding what is placed on it. Much of the Tohoku coastline sits on loose sandy fill and marine sediment that shifts, liquefies, and consolidates unevenly when loaded. A seawall 15 meters tall, pressing its full dead weight onto sediment that has not been treated, will settle differentially across its length, opening cracks in the base and rotating sections forward toward the sea. Ground improvement begins months before the main structure arrives. Crews drill vertical piles of steel or concrete to depths that reach below the compressible layers into bearing strata. Between piles, they inject cement-stabilized grout that permeates the loose sediment and binds it. Sand drains are installed to accelerate the consolidation of saturated layers under preload surcharge, essentially placing temporary fill on top of the treated zone and allowing the weight to squeeze out excess pore water before the permanent structure goes on. Only after instrumentation confirms that settlement has stabilized within acceptable tolerances does the excavation for the foundation pit begin. The foundation pit in sections where the geology is most demanding goes more than 20 meters below grade. Temporary sheet pile walls hold the excavation open while dewatering pumps run continuously to keep the bottom dry enough to work in. A lean concrete blinding layer is poured across the bottom to seal it before the main reinforcement cage is assembled. The cage is not prefabricated off-site in its final form. It is built in place inside the pit, with horizontal and vertical bar layers lapped and tied at spacings determined by the structural design, using epoxy-coated or stainless steel reinforcement in the zones most directly exposed to seawater infiltration. Standard carbon steel corrodes in marine conditions at rates that reduce a wall's structural life by decades. The decision to use polymer-coated or stainless reinforcement in the splash and tidal zones is not a premium choice. It is the minimum specification for a structure expected to function for a century. The concrete mix itself is specified for durability against chloride penetration, the process by which dissolved salt migrates through concrete and reaches the reinforcing steel, initiating corrosion from within. A lower water-to-cement ratio, supplementary cementitious materials such as fly ash or blast furnace slag, and air entrainment to protect against freeze-thaw cycles are standard requirements in the Tohoku wall mix designs. Each concrete pour is divided into construction joints at intervals of several meters to control thermal cracking as the hydration heat releases. A mass of concrete large enough to form a seawall section generates internal temperatures that can exceed 80 degrees Celsius at the core if poured monolithically, and the temperature differential between core and surface causes tensile cracking that compromises the chloride resistance the mix was designed to provide. Thermal management of the pour is as important as the structural design. If you are enjoying this video so far, please consider liking and subscribing, as this helps us create more videos like these in the future. Once the wall rises above grade, the ocean-facing surface is not left as flat concrete. Energy. Dissipation begins before the wave reaches the wall. Tetrapod concrete units, four-legged shapes that interlock with each other regardless of orientation, are placed in layers in front of the wall and across its base. Each tetrapod weighs between several tons and 50 tons, depending on the location's wave exposure. A field of interlocked tetrapods forces incoming waves to thread through a chaotic three-dimensional matrix that breaks up the organized water column into turbulence, spray, and smaller fragments before the residual energy reaches the wall face. A wave that strikes a flat vertical concrete surface transmits nearly its full momentum into that surface. A wave that passes through 2 meters of interlocked tetrapod armor arrives at the wall face as a fraction of its original coherent force. The wall still absorbs that fraction, but the fraction is survivable where the original was not. The geometry of the wall face also manages the energy that gets through. Vertical walls reflect wave energy directly back seaward, which can increase the amplitude of subsequent incoming waves through constructive interference. The Tohoku walls use sloped faces in many sections, angled to direct the water upward and over rather than rebounding it horizontally. Splash reduction ledges at the crest deflect overtopping water backward onto the landward face, where it runs down into drainage channels, rather than falling freely as a coherent mass. A wave topping a vertical wall at speed falls as a continuous sheet of water that can flatten structures on the landward side. A wave topping a sloped crest with a deflection ledge becomes a spray that dissipates most of its energy in air before reaching the ground. The distinction between those two outcomes is the difference between a structural engineering problem and a drainage problem. Harbors present a constraint that solid walls cannot solve. Ships entering and leaving a port cannot pass through a continuous concrete barrier, and keeping gates manually operated in a populated commercial harbor during a tsunami warning is not a reliable method. 2 gate configurations were developed for the Tohoku wall network. The first is a top-down drop gate, a steel panel suspended horizontally between 2 concrete towers above the harbor entrance. normally raised clear of the water to allow vessel passage, and released by hydraulic motors to descend into guide slots in the tower walls when a warning is triggered. The panel drops under gravity and hydraulic pressure, sealing the harbour entrance within a few minutes of the warning signal. The second configuration, used in narrower channels where overhead clearance for a tower structure is not available, is a bottom-up rising gate, a steel panel resting on the channel floor under normal conditions, lifted by hydraulic rams embedded in the channel walls when the warning signal arrives. Ships pass over it in its resting position. Under warning conditions, it rises to close off the entrance. Both gate types are connected to Japan's seismic monitoring system, which triggers a warning signal from sensors detecting ground acceleration, allowing gate closure to begin before the wave has traveled from its generation point to the coast. In Rikuzentakata, the wall was not enough on its own. The city lost roughly 80% of its residential area in 2011, and the topography that remained after the destruction was flat coastal land, sitting only a few meters above sea level. A 12.5-meter seawall provided a defined amount of protection, but placing residential neighborhoods directly behind a wall of that height on land that low meant a single overtopping event would still flood everything. The decision the city reached was to raise the land itself. A single conveyor belt system running 3 kilometers from the mountain slopes behind the city to the coastal plain transported earth continuously for 5 years, depositing enough material to raise the entire city center platform by 10 meters above its previous grade. The volume moved was equivalent to roughly 9 times the interior volume of the Tokyo Dome. The seawall was then built in front of the elevated platform. A residence standing in the rebuilt city center is now 22 to 23 meters above the wave that destroyed the previous city. The engineering here was not the wall alone. The wall was the last element of a layered system that began with the ground. The controversy over this system is structural, not incidental. Fishing communities along the Tohoku coast have been building their economies and their physical relationship with the ocean for generations. A wall 15 meters high does not just interrupt the view. It terminates the visual and physical connection between a community and the water that defines what that community does and how it organizes itself. Fishermen in several communities have formally opposed the walls on the grounds that they cannot observe sea conditions from their boats' traditional launch points, that the walls restrict tidal flow in ways that affect inshore fishing grounds, and that the false sense of security a wall provides may be more dangerous than the risk it addresses. That last argument is the engineering argument, not the cultural one. The walls built before 2011 in Kamaishi and elsewhere produced measurable behavior changes. Residents near those walls were documented as being slower to evacuate when warning sounded, because the presence of a wall created an expectation of protection that removed the urgency. The 2011 tsunami moved faster than that expectation could be corrected. Ecologists have pointed out that the construction footprint of a 400-kilometer continuous concrete structure along one of the world's more productive coastal zones involves disruption to tidal flat habitats, kelp forests, and the sediment transport patterns that maintain those habitats. Some researchers studying the Tohoku coastline have argued that mixed coastal forests, sand dune systems, and maintained mangrove zones provide meaningful wave attenuation at a fraction of the cost, and without the community severance that the concrete walls impose. Japan's program has not included large-scale investment in those alternatives. The program is a concrete program, and the time pressure imposed by the reconstruction mandate and the political urgency created by 2011 produced a concrete solution at concrete speed. The physics has not changed. The Nankai Trough, a subduction zone running southwest of Japan's main islands, is assessed by Japanese seismologists as capable of generating a magnitude 9 or higher earthquake with a probability of 60 to 70% in the next 30 years. The modeling of that event produces wave estimates that in some scenarios approach or exceed the height of the walls. Now standing. The walls are not designed for the largest possible event. The engineers who built them say so in the technical literature. The walls are designed for a specific range of wave heights, and for events within that range, they will reduce force and delay arrival by minutes. For events above that range, the walls will be overtopped, and the same 4 to 6 minutes that the wall's geometry provides as a time buffer for an ordinary tsunami event will still exist, but the wave energy arriving behind them will be different. $12 billion, 400 kilometers of concrete, 25-meter foundations, 30,000 workers across more than a decade of construction. The seawall is the largest coastal defense infrastructure ever built in Japan. It will not stop the ocean. It was not designed to. It was designed to change the arithmetic of a specific range of wave events by enough minutes that the number of people who reach high ground before the water arrives is measurably larger than it would have been without it. Whether that arithmetic holds when the Nankai Trough releases, whether the evacuation culture the walls are supposed to supplement is actually stronger or weaker with the walls in place, and whether the communities that live behind them for the next century will use the time those walls buy, is not an engineering question. The concrete is already there. What do you guys think? Is this a smart move from Japan? Let us know in the comments below, and thanks for watching Beyond Blueprint.